It's recording. We're on the air. It's live. Huh? Jeff, can you take a look at this? If I douse this, is it going to get too dark where it's recording?
It looks all right.
Looks okay? All right. It's fine then. All right, let's dig into this. This is fun stuff. This is kind of different, I suppose. I'm going to put a little cap on what we're doing. Hey, you know, my analogy from the beginning of class was that we're boarding this sailboat, whatever, and taking a little voyage. You know, we're about ready to pull into port. That's where we are now, right? We're just about done. In fact, as I said, this is it for our new material. These couple things we're going to talk about today. So the goal of this presentation is to introduce you to another world of computing, another world of analysis and opportunity. See, this wasn't even really an opportunity when I was your age, and recently I think has really gotten a lot of momentum behind it, high-performance computing. And I hope to encourage you to learn more about, I think it's a fascinating field, HPC. So some terminology up front, the alphabet soup, let's kind of get it out there. Supercomputing. HPC is high-performance computing. HTC, high throughput computing. CI is cyberinfrastructure. As far as I'm concerned, they're kind of all part of the same alphabet soup, and we're gonna more or less treat those synonymously in this presentation. Okay? Yes, there's some nuances that actually they're a little bit different in what they encompass and what they really mean. But for what we're talking about here, to get you all started, we'll use these things interchangeably. I'd like to acknowledge Henry Neiman. In fact, I got an email from him. We're going back and forth on some stuff just today. He's from Oklahoma University and Oscar, a supercomputing center. That's what that is, Oklahoma Supercomputing Education and Research. That's Oscar. And so parts of these slides here are from Henry, and I acknowledge his help with that. What is supercomputing? Well, supercomputing is the biggest, fastest computing happening right this minute. A supercomputer 20 years ago is laughable today. Supercomputer 20 years ago was the size of a room, big room, you know, and very noisy things. In fact, the capabilities of those supercomputers 20 years ago are equaled by one graphical processing unit that's about this big, you know, fit it in your hand today. So things have changed. So that's why when we talk about supercomputing, it is the biggest, fastest computer right now. Likewise, a supercomputer is the biggest, fastest yet, right this minute. So the definition of supercomputing is constantly changing, going up, 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 up. As a rule of thumb, a supercomputer is typically 100 times as fast as a powerful PC. Wow. Okay? Imagine that something that takes you 1 hour on a supercomputer could take 100 hours on a PC, if it runs at all. Okay? Take a look at this real quick, which is the fastest supercomputer and what's called Moore's Law. So the fastest supercomputer in the world is, we're measuring this in what's called gigaflops, right? So a flop is a floating point operation per second. Okay, that's a flop, and so we're talking about a gigaflop. And so we can measure them like that.
Is that a billion?
Yeah, yeah, right, so Moore's Law says that this is how things should be going, right? From 1992 on to 2007, you know, we'd be about 2010, 2012 here. But in reality, the fastest of supercomputers is about there. It's actually exceeding what's supposed to be happening following Moore's law. We're going to talk about why that is, kind of throughout the rest of this presentation, and why we're exceeding, why we, broadly, mostly it's them, the supercomputing guys, figuring all this stuff out and really making these computers work with tremendous performance. So what is supercomputing about? I think you're already getting the hint. It's all about size and it's all about speed. Big data sets, big computers, and everything's happening very, very fast. And that is, of course, in comparison down there to a laptop, right? As you kind of wind up and it might move along a little bit. And that's a nice analogy in the huge differences between these worlds. Let's talk about size. So many problems that are interesting to scientists and engineers can't fit on a PC. We want to analyze an enormous data set, a data set that is measured in terabytes, right? A data set that's measured in many, many gigabytes. To really analyze that, we don't have to just store it on a hard drive. To analyze it correctly as one piece, we have to fit it into memory. Now, how many computers out there have a terabyte of memory? Yeah, now there's all in the world of supercomputing, right? We're talking about how in the world do they get a terabyte or more of memory, right? So we'll talk about how that works. So usually because they need more than a few gigabytes of RAM or more than a few 100 gigabytes of disk space, we got to, in some cases, we simply have to go to the supercomputing or HPC world to get something done because it can't fit on a PC. Other than, the way that we do it, if we have a big data set, like that enormous data set I've been running literally for months on a PC. I got to check on what it's up to now. Hopefully it's about 60 to 70, maybe 80% done for me. What we're doing is tremendous amounts of I/O traffic, right? It reads in a certain amount of data, processes it, dumps it, grabs another set, processes it, dumps it, and does all this stuff and writes answers to memory so it can call it back up later on and analyze the preliminary answers together and do the averages, and you name it, right? That's why they're so darn slow, okay? Because of that constant barrage of input-output traffic to the hard drive. And relatively speaking, hard drives are terribly slow compared to working in memory, which is comparably terribly slow compared to working in cache. Right? The cache, the burst cache memory that you have is really, really fast. Speed. Many problems that are interesting to scientists and engineers will take a long time to run on a PC, which is what I was alluding to just a moment ago. Months, or sometimes even years. But a problem that would take 1 month on a PC might take just a few hours on a supercomputer. So what can supercomputing be used for? Generally, the different tasks that we assign to a supercomputer, or the type of jobs we give to those things, will fall under one of these categories, sometimes more than one. That is data mining, modeling, simulation, and visualization. Okay? So there's some folks doing visualization stuff here on campus, Donna, and you guys doing some visualization stuff, which is neat stuff. There's a growing world, especially in GI science, pushing the envelope on visualization. A lot of folks doing things modeling, climate modelers. A lot of that, of course, is geospatial in nature. Data mining, the big data, right? You've probably heard quite a bit about big data, trying to get at and find information in this, the needle in the haystack type of concept. And if you're interested in data mining, that's where Hadoop is very, very powerful, and that optional exercise I'll be giving you later this week. So, what is a supercomputer then? Well, it's a cluster of smaller computers. Each one is called a node, and they're all hooked together by an interconnection network called the internet. The interconnect. A cluster needs software that allows it to, allows those nodes to communicate across the interconnect. But what a cluster is all of these components working together as if they're one big computer. That's what the interconnect does. Takes all those small ones, puts them together, makes them look, act, and feel as if they're one computer, in other words, a supercomputer.
Like ording.
What's that?
Like an ording.
Yeah, yeah. Right. So this is a photo of Sooner from the Oscar. This is a fairly new supercomputer over there. It's a year and a half old, I think. So it has 1,000 CPUs, each of them quad-core, 4,288 cores. Okay? 8,800 gigabytes of RAM. So that's 8 terabytes of RAM. 130 terabytes of globally accessible disk space. What else is really cool here? It's running Red Hat Linux, which is interesting. It's a commercial Linux version. The peak speed is 34.5 teraflops. Right, that's going. Remember our little Moore's Law thing was measured in gigaflops? Right? So now we're a whole order of magnitude off that chart. And Moore's Law is not even close to what this thing is doing. Go ahead, Matt.
Where are the bottlenecks typically at in these systems?
The bottlenecks, yeah, when we tried to do some experimenting with a supercomputer at Texas Advanced Computing Center, and I worked with those folks down there, and the bottleneck is getting your data to it, okay? Which is then what?
Network.
The network, right? We had tremendous amount of trouble getting, you know, even what was it, 6 gigabyte data set, GIS data set, out to this TAC to try to do some analysis. That's huge. That's what a problem. Oh my gosh, it would take overnight. You know, no, it failed, something went wrong. So some of that is being fixed or has been fixed by Globus. How many folks in here have heard of Globus? Yeah. Globus Online, we've enabled one of our big servers here, a LiDAR server, to be a Globus endpoint. So that's typically how people download those big LiDAR data sets we have sitting out there, is through Globus. And I've been working with those guys now for a couple of years. That's a very powerful software too, and has sort of, well, it's reduced that bottleneck as much as humanly possible. Okay, but that's the bottleneck right there. I guess the other bottleneck, it's kind of a virtual bottleneck, is a lot of people don't know about this. Right? They say, well, I'm not at Oklahoma, so I guess I can't do it. Wait a minute, right? How many folks have heard of Exceed and the Campus Champion program, right? So I'm a campus champion, NSF campus champion for Idaho State University. There's 3 of us on this campus. And if you want to use a supercomputer for modeling, visualization, simulation, data mining, those sorts of things, start talking to one of the campus champions, and we can help you write a proposal. It's actually fairly short. It's all done online, to request allocation time on some of these supercomputers. And there's supercomputers scattered all over the United States. We'll work with the people and then say, hey, here's the problem that we're trying to solve in our data set. What's the best supercomputer that we should be doing this on? They can match us up or match you up correctly and get you some allocation time on those machines. Wonderful thing is it's funded by NSF and it's free. Okay, you spend some time on your proposal. Hopefully you get funded for it, and they'll give you X number of hours on those big machines. Okay, so that's why I say it's a virtual bottleneck, simply because people don't know about the possibilities. Okay. Any questions? No. Okay. So quantifying a supercomputer. So far we've been talking about flops, right? But there's other ways of quantifying a supercomputer. There is the number of cores, right? How many cores are on that machine? What's your workstation got? 4, 2, 12, maybe 8. You know, how many of you guys?
I got 32.
32. Do you remember what? Do you remember what Oscar had just a little bit ago?
Which one's Oscar?
Oscar is
4,400 or
Oh, yeah.
4,288 cores. Same thing, we're talking about the same cores, right? But even Oscar pales in comparison to this monstrous machine, the biggest supercomputer in the world right now. I think it still is considered that, with 300,000 cores. I just sent out today to GIS users listserv that the Shodor Foundation, they did a workshop here a couple years ago at ISU that I helped set up. We have people from all over the United States, all over the world actually, people from Greece and stuff come in for this one. And they only do so many workshops per year. They did one here at ISU that myself and Nancy Glenn organized. Nancy's now at Boise State. But Shodor is funding students to work on blue waters. You know, if you got a project or you want to get involved with blue, you don't have a project, you just want to get involved with the supercomputer, there's a chance to apply right now for quite a number of months. I got it opened up to get some experience working on blue waters. Cool deal, right? So a number of cores and the flops, teraflops, gigaflops, are pretty much how you quantify a supercomputer. There is an ISU cluster here at ISU that has 800 cores, and that's the largest one I know of here at ISU. INL has some stuff in the thousands, but you see, you know, that once you jump out to exceed blue waters and all these other things, you're talking about tens of thousands typically of cores. So big machines.
Can you also, like, you rent Amazon servers now, right?
Yeah, you can do Amazon stuff if you want to pay for it.
Right.
Yeah.
So they'll scale it to whatever you need.
Yep. I don't think Amazon does not have these capabilities. Not even close, I mean. So, but you can do some stuff. The other thing is we do have, you guys are going to work on Mr. Shorty today. It's a little Linux machine that we're actually, well, we're clustering some bigger stuff together for the Hadoop. But if a person just wanted to test an algorithm, right, and you need a Linux box that has numerous cores on it, you could use the one here at the GIS Center. You could, you know, work with other people that have a small cluster. And if you can get your algorithm to run on a small Linux cluster, you should be able to go to a similar Linux cluster on Exceed and just run a big job all the faster because of all the cores that are available. Okay? So that's why, you know, a number of people here at the university are trying to build small clusters to use as a sandbox to let people then scale up to Exceed type of supercomputers. So how does a cluster work together? Why are these things so darn fast compared to our PCs and our servers? And the answer there is parallelism. Well, let me explain what parallelism is. Parallelism means doing multiple things at the same time. Here we have one person. This could be the best fisherman in the world. One person fishing. Right? He's going to catch some fish, but I'll guarantee it's going to be less fish than a whole bunch of fishermen fishing all at the same time. Right? Some people might strike out, this person's me, I didn't catch anything, but everyone else caught a few fish, which is way more than this guy. Okay? Less fish, more fish. Imagine that this is, you know, your single CPU PC. This is numerous CPUs, each with numerous cores, working all at the same time on the supercomputing side. So to understand parallel processing, we can use this jigsaw puzzle analogy. Let's walk through this. In serialized or serial computing, aka Windows type of things, the old DOS type of things, serial computing, we can compare all this to building a jigsaw puzzle by ourselves. We take a 1,000-piece jigsaw puzzle, dump it out in front of us, in front of, you know, one person, and we just start working it. Right? We take one piece, hook it up to another one, and keep on going. That's serialized or serial computing. Let's just agree that we can finish that jigsaw puzzle in 1 hour. We're good at jigsaw puzzles. We can do 1,000 pieces in an hour. Wow. Right? Well, I'm not good, but whoever this is doing this is really good. Now let's talk about what's called shared memory parallelism. So let's say we have Scott sits across the table from you. He's going to start working on half of the puzzle while you work on yours, on your half. Right? You just take some pieces and start working. Once in a while, you're going to reach into the pile of pieces, and you'll both grab accidentally the same piece at the same time. You'll contend, what's called contend, for the same resource. This is going to cause you what? To slow down, right? Because, oh, sorry, you can have it. And Scott says, oh, no, you can have that piece. You did touch it first, or whatever, okay? But there's a contention for resources. That's overhead. And from time to time, you're going to have to work together. Hey, I got a big chunk over here, and it looks like that fits into your part, right? Oh, let me slide this together. Here, help me slide this together. Now you're communicating, putting these two parts of the job together. Okay, so this communication at the interface between his half and your half is going to take up some time also, kind of more overhead. Contending for resources, communication at the interface. So the speed up will be nearly 2 to 1. There's two people working on one job, but not quite. Together, let's say it's going to take about 35 minutes, 32, 33 minutes, instead of 30 minutes. All by yourself, you did it in 1 hour. We take two people, we say, well, it should get it done in 30 minutes. But because of the overhead, contending for the same resource and communicating at the interfaces, we're going to say it's going to take 35 minutes. Okay? The more the merrier? Well, now let's put Paul and Charlie on the other two sides of this table. Each of you can work on part of the puzzle, but there's going to be a lot more contention for the shared resource. And a lot more communication at the interfaces. Hey, you got a piece of a little white thing that looks like this and this and this, all that kind of stuff. So you will achieve noticeably less than a 4 to 1 speed up. But you'll still have improvement. Maybe something like 20 minutes is required instead of the initial hour working on it all by yourself. But you won't be at 15 minutes, which is the 1 hour divided by 4. Then there's a point of diminishing returns. If we now put Dave, Tom, Horst, now this is the names that Henry threw in there, Brandon at the corners of the table, he has an interesting sense of humor. There's going to be much more contention for the shared resource, a lot more communication at the interfaces. The speed up is much less than, and we'd be lucky to get a 5 to 1 speed up. And you can see that by adding more and more workers onto a shared resource, that's the bottleneck here, we have a shared resource, is eventually going to have diminishing return. Let's talk about this here just for a little while before we go on. That's Amdahl's law. If you're interested in this, you can go to this website that's cited right here. So on our x-axis, we're showing the number of cores that are on this computer. And along the y-axis, we have CPU utilization. And in the world of supercomputing, you know, I sat in on some of these meetings and talked with these folks. Something like Blue Water's, I think the last I saw was Blue Water's price tag was in the several hundred million dollars. Several $100 million for Blue Waters. And it will be functional as a good supercomputer for about 5 years. So if the people who are owning and running and paying for the bills of these supercomputers are going to have money to buy a new supercomputer when this one's, bit the dust, what do you got to do? Think of your ROI, TCO. You just invested let's just say you spent $300 million on this thing. It's going to have a 5-year lifespan. How do we make sure we have money to buy a new supercomputer after 5 years?
Rent it with a premium and then sell it when you're done.
What are we doing again now?
Rent it.
Rent it? Oh, what are we renting?
Time.
Yeah, we're renting this allocation time, right? So as I said earlier, Exceed, you can get it for free. Who's paying the bill? NSF's paying the bill, right? Okay. So, so we rent that time out. So what do we want to do? We have, you know, X number of hours in a given day, a given month, a given year, multiply that by 5. This is how much time we got now. How are we going to ensure that we make some money to buy the new one? Just kind of, whoever wants to just goes on it, you know, what's the deal? What do we really got to make sure happens with that time?
Do you charge them appropriately?
Well, you have a break-even point, you know, whatever you're going to charge, you got to recoup your costs, and then
Right.
whatever it's going to cost you to buy that next machine, however more advanced it is, however much more
Right.
dollars it's going to cost
So
you.
let's say we figure out those number of hours, divided into the cost of the new one we got to buy. So now we know that each hour is going to cost this much. What do we got to really make sure happens now?
That you don't have any lapse time.
Yeah, we got to make sure we sell every hour. Because if every hour is worth $1,000 and we don't sell it, that's bad.
Do they round up on things like that? Like if you only use 1 minute of your last hour, they charge you for that whole hour?
I don't know about that. You'll be given, you know, what you'll do, you know, to exceed, you'll be given X number of hours as your allocation after you write your proposal. The federal government essentially is paying for that, okay? And when you run out of your hours, you're either flat out done or you put in another proposal for some more time. So those guys are getting money, okay? Now you can be denied, like you can say, I want to work on blue waters. Well, if you need 500 cores for your job, or 5,000 cores, or 50,000 cores for your job, you're not going to be given blue waters. Because blue waters is being reserved for people who need 300,000 cores. Okay? But what's nice about that, those people who want and need 300,000 cores, they're flocking to blue waters, which means Lone Star and so on and so forth, and Oscar with a couple thousand cores are like, oh, what are we going to do? We need to sell our time, right? Oh, we'll get this into the Exceed system, right, and get our time bought and paid for through Exceed, right? So you're going to have access to supercomputers. That's a good deal. So what we need to do is we need to keep those cores busy. Every one of our cores busy, our CPU is busy 100% of the time for 5 years or whatever our cycle is going to be. So we want utilization flatlined up here at 1. Okay? So what this is showing me that is if we have a serialized process, this is 30%, I'll just show you this. This is 30% serialized application. Most of the applications we run are darn near 100% serialized. Okay? And what we're seeing here is that if we have only, 1, 2, maybe 3 cores, maybe 4 cores, we can keep that CPU pretty darn busy in this 30% serialized scenario. If we go into 20 cores, 40 cores, 50 cores, now at 50 cores we are only at about 10% CPU utilization. In other words, only about 10% of that computer's resources are actually being used. The rest of them are idle. Now, why in the world would I spend $300 million on a machine where most of those cores are sitting idle? I am really wasting my money, right? In fact, I should have bought, you know, a machine with about 4 cores on it. So we don't do that, right? The supercomputing world is not done with serialized code. It's done with what's called parallelized code. So let me show you some more stuff here. If we reduce the percentage of serialized code down to, here's a quarter of a percent, now we're getting close to 100% utilization all the way up to 100 cores. And if we run this thing out and even further reduce the percent serialized, we can just about get this thing to flatline at 100% CPU utilization. The only way to get that is to use parallelization, okay, which is a whole other world of writing programming. And unfortunately, The programming languages that you need to know to do this stuff is C, not C++, not C#, or Fortran, stuff like DWU, Dr. DWU teaches here, right, occasionally. Java, Hive, Pig, Jackal, those sorts of things, Java type of things in the Hadoop world. And there is a parallel Python. I haven't seen much of that really catching on. But the biggies are C and Fortran. Go ahead.
I was just looking through the slides. You don't really mention performance per watt. You ever have discussions about that?
Oh yeah, you know, wow. I sat in on a presentation at an Exceed conference when it was called TerraGrid in Salt Lake City. I thought, oh, this sounds kind of interesting. They're going to talk about these algorithms, and they're going to compare 3, 4 algorithms, right? And these guys, these computer engineers and the programmers, their kind of life is taking code and getting it to run milliseconds faster. A few milliseconds faster is an enormous success. Why is that? Because we can get this job done and pack more jobs into this supercomputer, therefore get the money to come back all the faster, right, to buy the new one. So, yeah, everything is a consideration of these guys. Heat factors and energy consumption, if we can get it to run with less energy consumption, right, we can pay the bills all the easier. Yeah.
Like all those new ARM-based servers?
Yeah, right. Yeah, so it's a crazy deal. It's like, wow, you guys are worried about this? Because in my mind, right, you just ran the thing, right, and now you're going to run it again and try to get a millisecond faster. I only care that it's done. You know, give me the answer, right? But it is awful cool. It really is kind of cool stuff. Let's look at something a little bit different now. It's called distributed parallelism. We're going to set up 2 tables, 2 separate tables. You're going to sit at one table and Scott's going to sit at another table. We're going to put half of the puzzle pieces on your table, half of the puzzle pieces on Scott's table. Now you can work completely independently on your part of the puzzle. You don't have any contention for the shared resource because there's no more shared resource. This is your pile of puzzle pieces, and that is Scott's pile of puzzle pieces. But the cost for communication is going to be much higher, right? Because you need, the ability to split up that shared resource correctly. So you got the right half of that shared resource. Let's say the bottom half of the puzzle is yours, the top half of the puzzle is Scott's. And if you don't divide that up correctly, then pretty soon you're getting up from your table and going over, I want to see what you got in your puzzle, right? That's terrible. So that that process of cutting up the shared resource correctly is called decomposing the problem. Okay, and there's an overhead on distributed parallelism. But if it's done correctly, in other words, the code is written really well to do that, then you're going to have some fantastic performance gains on that solution. And you know, as you add more people to it, you know, more cores working on it, you're going to come very, very close to, if you have 2 on it, to 30 minutes. 4 people on it, 15 minutes, based on our previous scenario. More distributed processors. Okay, it's easy to add more processors in distributed parallelism. But you must be aware of the need to decompose the problem correctly and communicate among those processors. There's 2 ways that we communicate or send jobs out to various processors. One is called MPI, and the other is OpenMP. Okay, it's multiple processor coding. That's all that's really doing. And it takes care of this core is going to be busy doing this job. It's not going to let them just sit idle and do something. As soon as they get finished with a job, and that job, the return comes back to the parent processor, that core is going right back to work on another job. See? Let's see, and load balancing is important also, which is what I was alluding to, keeping each processor working evenly. There are different kinds of parallelism. There's what's called instruction level parallelism, shared memory parallelism, or shared memory multi-threading. And I put some of those in white because we're going to revisit those a little bit more throughout this presentation. There's distributed memory multiprocessing, or distributed memory parallelism. There's GPU parallelism, which we'll touch upon in just a little while, and hybrid parallelism, which is combining any of the other ones above. And if you're doing that, that's called a hybrid parallelism or parallelized approach. Why parallelism is good? We can look at the trees and understand that parallelism is good here, because as the number of processing units working on a problem grows, we can solve the same problem in less time. We can also look at the forest type of perspective. Same analogy, as the number of processing units working on a problem grows, we can solve bigger problems. Okay? So that's why parallelism is good. We can solve the problem in less time and solve bigger problems. Some jargon for you. Some of the stuff we've already thrown out. Sometimes in the world of supercomputers, it's a little bit different than what we're used to with the Windows world. Threads are execution sequences. The single memory area processes are execution sequences within their own independent private memory area. Multi-threading is parallelism in the world of HPC via multiple threads. Multi-processing is parallelism via multiple processes. So that's the forest and the trees. That's the forest and the trees. Okay, we were just talking about. Shared memory, okay, I got them back in white again. We talked about it just a minute ago. Shared memory parallelism is concerned with the thread. Distributed memory is concerned with the processes. Hybrid, obviously, with both. Basic strategies on data parallelism. This is where each processor, now pay attention to this, follow this along carefully. Each processor does exactly the same task on its unique subset of the data. Jigsaw puzzles, big data sets that need to be processed now. Okay? I've got my chunk of the, it's all been cut up just appropriately for me. This is data parallelism. I work on my part of the puzzle. Task parallelism is where each processor, or core, does different tasks on exactly the same set of data. Different tasks, exactly the same set of data. Every core is working with the same set of data, but doing something different with it. And here we're answering which algorithm is best, which one's fastest. Assuming they all get the right answer, too. We might find out, whoops, this one's just wrong. It might be fast, but it's wrong. So let's look at an example. This is called an embarrassingly parallel scenario. And it's an application or a process is known as embarrassingly parallel if its parallel implementation is or can be straightforwardly broken up into equal amounts of work per processor and has minimal parallel overhead communication among processors. In other words, I give you your job, you could just do it all by yourself. You don't have to be talking to anyone else, and that's about it, right? Embarrassingly parallel applications are also known as AKA loosely coupled applications. Monte Carlo methods. This is a nice example. How many folks have heard of Monte Carlo or Monte Carlo simulations? Yeah. Okay. So Monte Carlo methods are ways of simulating or calculating actual phenomena based on randomness within known error limits. In GIS, we use Monte Carlo simulations to calculate error propagation effects. A number of years ago, Jackie Langeal worked here at the GIS Center, and she and I worked on a process where we did hundreds of iterations of we're working with Landsat imagery. The whole goal of the process was to test Monte Carlo simulations. and I didn't even forget what the heck the little task we gave it. But she became known as the queen of the batch file because she could set up, by the time she was really good at this, she could set up a batch file in Adrisi, the satellite remote sensing software, and just let it run, sometimes like a week at a time, and it would just go process after process, you know, and worked out really well. So what we might want to do in GIS, let's say that we're looking at modeling landslide potential, okay, landslide potential. And one of the key pieces of data, GIS data we're going to use for this will be a slope model, right? Because the idea is the steeper the slope, right, this is the assumption we're going to work on, the steeper the slope, the more likely we are going to have a landslide following a wildfire or something that removes all the vegetation, let's say, right? Is there any error in our slope models? Yeah, there is. I mean, those DEMs from which the slope models are derived are not perfect, right? There's going to be some error to those things. So if we know or we can quantify the error that the slope is off by plus or minus 2%, let's say, potentially off by plus or minus 2%, then what we could do is we could run one of those landslide models with a slope input layer, exactly as we received it from USGS, whatever the default value was, right? We could run it a second time by varying the slope within 2%, right? We could introduce a randomization process where each of the slopes changes by 2%, or we could go back to the elevation model, randomize on that, and then generate a brand new slope, right? Run it through the landslide potential model once again. A second iteration, do it again, a third iteration, fourth, fifth, sixth, 100th, right? Which one is the most correct of those 100 iterations that we just ran through? Is any one more correct than the other?
They're all the same error, right?
They're all working with a known error of the slope model. So the answer is they're all equally correct. So a lot of folks, they say, oh, no, the one I got from, the one I downloaded from the GIS Center's website, or the one I downloaded from USGS, that's the right one. And every other one is a possible scenario, but it's not correct. No. It's all within known error, and they're all equally correct. So every one of our 100 iterations is equally correct. And then what we might want to do is we might want to say, how often does our final answer on landslide potential change, right? Because we're randomizing within known quantities, but if the landslide potential really doesn't change, then we have high confidence that we've got a good answer here, right?
Can you also use that to kind of test the stability of your algorithm?
Oh yeah, sure. Yeah, because hey, maybe it runs perfect with this set of data, but give it a little bit different data, oh, what happened now, right? It bonked out on me, sure. Great way of doing it, right? So Monte Carlo simulations are typically, as you can see, embarrassingly parallel, because this model that's being run, the landslide potential model that's being run with one version of slope, doesn't have any input to the second landslide potential that's running with a completely different version of slope. See that? They're running absolutely independent. At the end, there may be some data written that says your landslide potential for run number 1 was this, for high potential and so on and so forth. And you might do some comparisons, but usually that's output, and the comparisons are being done by the person looking at the answers in the, essentially like a spreadsheet maybe, right? Everyone following me? We good? Okay, so here's what we were just talking about. You randomly generate a large number of example cases. Each of those cases I called iterations. In the supercomputing world, they like to call those realizations. And then we compare the results of these realizations. If the average, essentially the mean, median, and mode of those realizations converges, In other words, your answer doesn't change with each new realization. It doesn't change substantially. Then you can say the Monte Carlo simulation can stop. We've got confidence. We've got good data producing a good risk model or something like that. Monte Carlo simulations are embarrassingly parallel because each realization is independent, as I alluded to earlier, of all other realizations. Okay, so is this example, is this, what I just talked about, this Monte Carlo thing, an example of data parallelism or task parallelism? Just shout it out. Task parallelism, why?
Data.
With the same set of data.
They're all working with the exact same set of data, not a subset. There you go, perfect. Each processor does a different task on the exact same set of data. Right on? Yeah, you got it, same set of data. Questions so far? We good?
The
Go ahead.
the Northwest Knowledge Network we've heard about on GIS Day.
Yeah.
I can't remember if he said if they had any supercomputing capabilities. Do they act more or less just a large data storage?
It's a large
facility?
data storage, not designed, as far as I know, I've been working with those guys for some years, not designed for processing, designed to store data. It's big, it's 250 terabytes, I think. Yeah, lots of data space, but that's what that's designed for, a repository of data, not processing place. Anything else? Good. How are we doing over there, Bernadette, Alex, Bruce, and Daniela?
We're good.
Good, good.
Nobody.
All right.
So far.
All right. Well, hang in there. We're going to keep going. A bit more to know. This is just kind of fun. What is a GPU, or just short, GPU? And subtitle there, thank you, gaming industry.
Sounds like a topic on
Graphics processing.
what's that show?
Jeopardy?
Jeopardy.
Yeah. What did you say, Matt?
It's a graphics processing unit.
Yeah. What is it?
Oh, that's what it is.
That's what it is, yeah. It's an accelerator. Not that kind of accelerator, right? In HPC, an accelerator is hardware whose role is to speed up some aspect of the computing workload, okay? Because, as I said earlier, hard drives, they seem that they're pretty fast, storing data, retrieving data for us, but they're quite slow compared to the CPU, right, that's running live in RAM, which is relatively slow compared to the burst cache we'll have on those machines. But all of those things are relatively slow compared to accelerators like graphical processing units. So in the olden days, I don't know if folks remember this, maybe Alex or Bruce or Bernadette, along with me, I remember this. Sometimes computers had floating point accelerators, aka the math coprocessor. It was a funny thing. My dad, he bought a brand new computer one year, and he got this 8386, okay, aka 386. And about that same time, I bought a 386, but I had to have the math coprocessor. Mine had to be faster, you know? So that's what that was. That was an accelerator back in those days. I'm not even sure it really did much, right? But, you know, it was a selling point. Why accelerators are good? Hey, they make your code run faster. That's good. Fast is good, I think. Why accelerators are bad? Well, they're expensive. Well, at least they used to be. And they're more expensive than just your standard box. They're harder to program. NVIDIA is definitely the leader in graphical processing units and this whole world of using GPUs for supercomputing processing. And there's a language that's called CUDA that you use to program to essentially have your processing done, whatever the job is. It could be that Monte Carlo simulation we talked about. Instead of having it processed on the CPU, on the motherboard, on that sort of thing, process it on the GPU. But to get it to do that, you have to write your code in what's called CUDA, different programming language. Now the problem with that is your code may not be portable to other accelerators, So the time that you invest in programming, you're actually programming for this machine. And if you move it to that machine, it may not work. Because some component of the hardware on that machine isn't identical to this machine. So CUDA can be extremely particular about the full makeup, the hardware of the machine that it's written on. That's why accelerators can be bad. The king of the accelerators is the graphical processing unit. And well, that one's an ATI over here. But the king, the leader there is NVIDIA, and they have an entire branch of their company that is dealing with supercomputing, not using the GPU necessarily for graphics, but for processing, making these things work that way. Why GPU, graphical processing units? They were originally designed to accelerate graphics, image rendering for games. Essentially, that's the truth. They were designed for gaming, right? Because the computer gamers, the Alienware folks, they said, man, this is too slow. Lag, it doesn't look right, it doesn't look fluid, you got to fix it. So NVIDIA got involved, said, we can fix it, we'll do this, we'll do this. Hey, you guys willing to pay the bucks? Sure. People who are willing to pay $5,000 for a Alienware gaming computer instead of $400 for PlayStation 4, right? Willing to pay $5,000 over here, well, you're paying a lot of that because of the GPU that you're having stuck in that thing. So it worked out for NVIDIA and also for ATI to put some development, lots of development money into this. So they became popular with gamers because they produced better and better images, lightning fast refresh speed. Looks like a movie. Looks beautiful, right? As a result of all that development, research and development that's already been done, the prices have become really reasonable, ranging from a couple $100 for a low-end GPU to maybe $1,000, some dollars for a very high-end graphical processing unit. Now these guys produce some heat though. We have Alienware here. I have an Alienware that I bought for my son also at home, and he pushes that thing. It's an overclocked machine, so it really goes. It's getting old now, so it's not as fast as, of course, it seems like it used to be. But we put in the liquid cooling system because, wow, the heat is incredible in there. I should run it right here, And now let's talk some more, Right? Wow, it's crazy, So you got to worry about that sort of stuff. All that circuitry moving those electrons so fast will produce some heat, right? And you got to keep it cool. Otherwise, it won't run so fast, and it'll eventually burn out. GPUs just do arithmetic, though. That's how the images are rendered. And all that arithmetic really is floating point math. So once somebody figured out, hey, these things are just doing floating point math. How can I get into it and get it to process my numbers fast? And that was when CUDA was born. Interested? Curious? Well, to learn more or get involved with supercomputing, there's a host of opportunities awaiting you. Get to know your campus champions. Here at ISU, it's myself leading the bunch. Randy Gaines, who's the CIO for Idaho State University, is the second. And then Ben Nickel is relatively new. He's been doing it for a couple of years, though. We're the three campus champions. And if you have questions, you want to get involved, you want to get allocations, talk to one of us. We can start you down that process of writing a proposal and hopefully getting you allocation time on one of these big machines to do your research. Hopefully that can happen for some folks. Ask about internships. This is the Blue Waters. What does the rest of this stand for? I don't know. But that's the one I was just talking about. It's usually announced about this time of the year. So as an internship, and there's others besides Blue Waters, but that's the big one going on right now. Learn C. Not C++, but C. Or Fortran. Fortran 88 or Fortran 90. Learn Unix. Learn Linux. And the exercise today, actually, I'm trying to demystify Linux, make it so it's not so darn difficult for folks to figure out how to use this thing. So you're going to be using PuTTY, which is a secure shell type of little application. You're going to hit Mr. Shorty. You're going to do some simple stuff on, command line on your Windows machines first, then you can do essentially the same thing in the Linux world, Unix world, on the machine we have called Mr. Shorty. And you're going to be on a Ubuntu Linux machine, doing all the same stuff. And you're saying, this isn't so hard. I can get files, I can move files, I can create stuff, I can look at this. That's what you're going to do. And I think you'll come out of that saying, hey, this isn't so foreign, right? It's not too bad at all. And that'll be your first steps in learning Linux. And I'll encourage you also to think about some of these advanced programming classes that are offered occasionally here at Dee Wu teaches, and she does Fortran. Any questions? Wrap this part up. Go ahead, Matt.
Have you ever investigated Bitcoins?
Oh, what now?
Bitcoins?
No.
It's, I don't know, some new currency that's
Oh.
not government regulated.
Oh.
But it works on supercomputing, basically. You get little tasks and stuff for people that, they have a job that you need to do, like fold some protein or something.
Okay.
Put it out there. And the group picks it up, and if they can, crush the numbers and stuff, they get so many Bitcoins, which are actually worth a certain amount of money. But the problem is you can't just do it by yourself because the electrical overhead will, deplete your wallet. So you got to team up with a couple people, computers, you distribute it among them, and as a team you accumulate these things and stuff.
Okay,
It's
yeah.
kind of interesting. But it's
So-
all supercomputing.
Yeah, that's cool. That's cool. The on this machine, in fact, all these machines here in the GIS Center's classroom, B19, we have a application running called Boink. You may have seen it sometimes. Boink will start up if it's idle for a while, and we signed up with Boink, and I think it's Boston University. They're running climate change models, and they're using computers all over the world that sign up like ours, right? And we do processes for them for free. So this machine's on, and it's not doing anything. It'll go to work for Boink, and it processes global climate change models for them, sends off all the results, but using this CPU. I think kind of a similar thing, except there's no currency involved.
Yeah, it's like distributed supercomputing.
Yeah, very distributed.
Yeah.
Yeah, that's interesting. Yeah. What's interesting, they have a top 500 list of the fastest supercomputers in the world, and Henry sent me this little article that said that the Department of Defense, U.S. Department of Defense, has now got one of its supercomputers in the top 500. And the fun thing about it was that it is, they interconnected, remember interconnect? They interconnected 1,400 PlayStation 3s, right? I think they reprogrammed them, right? And what they're doing is using that cell-based processing that PS3 was very famous for, really powerful stuff. And that made it into the top 500 for the world, right? So it's like, man. And then you do the number crunching, 1,400 times what, 400? Well, that's still pretty expensive, right?
There's 7 cell chips in each PlayStation.
Yeah. Yeah, and it was going fast. Their teraflops were way up there. Really go, And they just left them in the regular cases. They showed pictures of these like stainless steel racks of PlayStation 3s, this one after another, all the shiny Darth Vader black color, Kind of interesting. But of course, they say you'll stay in the top 500 for about 6 months, and then you'll, after a couple cycles of their looking at it, you won't even be on the 500 anymore. You drop below. Interesting, huh? How that fast that world changes in what they call big iron. Okay, so we have another presentation I want to do with you, which is the cloud computing. But usually when I do a couple of presentations like this, I like to break it up for a little bit. So it's 10 minutes after 3 right now. Let's go ahead and just take a 5-minute break. We'll come back in, start back up at 3:15 with the second of the presentations for the week.
I'll grab my jacket.